Thank you all for tuning in to our webinar today. My name is Alyssa Welch, and I'm the Marketing Manager here at AMT. Today's webinar will be presented by AMT's Chief Technology Officer, Luis Folgar, and PostPro3D's Director of Strategic Business and Advanced Manufacturing Solutions, Justin Swartz.
I'm Justin Swartz. I've been working at PostPro3D for the past about a year and a half. Previous to that, I was an engineer in a variety of roles at 3M for about 12 years. And my role at Forecast is to enable additive manufacturing to start stretching into the production environment. Here at Forecast, we've actually been recently acquired by GKN. That was as of January. GKN being a very metals-focused company with materials background as well as component creation, was very tied into the automotive industry, and Forecast being a very plastics and prototyping-oriented business, have now combined to start looking towards what will build the factory of the future, how to build those strategic industrialization solutions, as well as that dream state of the digital distributed manufacturing. So we're uniquely positioned to lead the AM market here. How we're doing that is through a variety of different services and offerings. We have the materials side, heavily focused on the metals at the moment. We have the engineering portion, where we assist customers with our design for additive services, as well as reverse engineering and simulation. Then we have kind of our baseline, which is the prototyping. This is pretty standard amongst the 3D printing industry. And where we're moving, which is the production side, starting to build up to millions of parts, if not more, in weekly or monthly quantities or timelines. Included in that is a variety of different certifications depending on what your industry or application may need. We are both local partners as well as available in the global market. The PostPro3D portion is headquartered in Carlsbad, California. The GKN additive side is located in Bonn, Germany. We also have locations in Auburn Hills as well as China. In terms of the range of materials that we offer, we have plastics as well as metals. We're heavily tied into the MJF HP technology. So this will be part of our presentation today that we cover, but we also have urethane casting as well as some of the more traditional 3D printing like FDM and SLA. On the metal side, we have the traditional laser technology as well as some of the binder AM that's coming from HP's metal jet machine. So we're early partners in that process, as well as the more traditional manufacturing methods, the MIM and powdered metal center parts. For this presentation, what we're going to focus on is what is sterilization, how do you measure it, and just a basic walkthrough of, if you want to qualify a 3D printed component and it needs to be sterilized, what does that generally look like? So where we'll start is the basic, definition of what is sterilization. This all pretty much comes from the CDC infection control website, and it breaks it down into three simple categories. There's on the lower end, the cleaning portion. In the middle section, there's usually disinfecting, and then on the higher end of having no organisms or any kind of growth is the sterilization side. So to break that down a little bit further, cleaning is just the removal of germs and dirt and impurities on the surfaces. So this is kind of what you would do at your home with a vacuum cleaner and wiping down surfaces. Usually it's the combination of friction and some sort of fluid, as well as a soap or detergent. These are pretty standard things, and the whole idea here is to actually get rid of as much of the kind of surface material as possible, so that the next stages in the disinfecting process can be more effective. Common types of equipment You see ultrasonic cleaners and dishwashers and stuff like that. Next up is disinfection. So this is when you actually start eliminating pathogenic organisms, but not necessarily bacterial spores. Depending on your industry and your application, it may be important to address this in different ways. One thing I found during my research is that antiseptics, which we commonly think of in the medical industry, that's only used for living tissues, and typical disinfectants we think of for cleaning a house is primarily used for inanimate objects. The idea here is that typically you're using some sort of chemistry to eliminate the microorganisms. And depending on the situation that you're trying to actually sterilize or disinfect, it can have a certain level of efficacy. There's some other options in there, including ultraviolet radiation and pasteurization. So there's ways to approach these depending on your application. Next up, sterilization is actually a process that destroys and eliminates all forms of microbial life. This is what you typically think of when you view healthcare and surgical equipment. The idea there is that you don't want anything to go into a body that shouldn't be there. And these tend to be the more extreme processes. Autoclave is a common one, and that's a form of steam sterilization under pressure. Ethylene oxide is another form of this. Those are the two that commonly come up in the initial research of these technologies, but it also depends on the material that you're sterilizing. Metals are a little bit simpler compared to plastics, where heat and moisture sensitive items typically require some lower temperature sterilization technology. In terms of measuring the sterilization and the efficacy of it, it really depends on the industry that you're in and the risk that's being applied. They have a variety of different ways of evaluating this. Speaking in general terms, basic cleaning, that typically is just done with visual. If you see an object and it's got dirt on it, obviously it's not clean. The other aspect of this is, if you dive a little bit deeper, is the actual material property and performance changes. So if you were to go through a sterilization cycle, how does it actually affect the part that you're working with? Again, metals, it's typically not as much of an issue, where plastics it is. And then the typical case for most sterilization, where there's more extreme conditions and requirements and risk assessments in play, you're going to see biological indicators and chemical indicators. And the idea there is that you will be able to identify if there's some sort of microorganism potentially growing there, or that a certain chemistry is reacting the way that is approved by those industry standards. All right. Next up, if we were going to walk through sterilizing a 3D printed component, essentially you would start on the left-hand side by picking your application and identifying an industry standard to kind of use as either our guideline or as the actual guideline for your product. From there, what you have to do is you typically verify the technology and material. Sometimes the OEMs actually supply some of this information, depending on what your actual application is. There might be information available to you. In some cases, depending on what you're doing, you actually have to do your own studies and confirm and verify that this is going to work for your situation. From there, you typically move on into the kind of specific design and production process. So that's when you evaluate maybe how a component works within a system and some of the potential issues it might run into. And that's where things like part finish and part application start getting more detailed. And then the last component to this, typically especially in the healthcare industry, is the documentation of all these results, and then the lockdown of the process. So essentially, you're verifying that your materials and technology are acceptable for the application, your design is acceptable for the application, and has a repeatable process, and then you document to confirm these results and present those to whatever resource that needs to approve this. So if we look at it from the perspective of, we'll say, the MJF or HP's MJF technology, what we try to do is we look at the whole spectrum, the entire value stream of the process. In this particular case, we're primarily interested in the printing and the materials. But as you go through the entire walkthrough of a potential production item, you want to include controls for, the processing, how the files are handled, how the files are sent to the machines, as well as the post-processing. And this is where AMT's process provides some new flexibility where we may not have had it before. And then kind of on the other end is the quality control. This is where you would end up doing all your testing and getting your results from either the printing or the finishing, starting to understand the process for your specific part, as well as having the systems in place to make sure that we're building in the feedback that you need to have the traceability and that you're meeting the specifications for your end product. And then the last thing, usually the last thing anybody thinks about is how's this packaging actually going to be set up, and how are the parts going to be sent to the customer, identifying best practices for that area as well. So to keep going, the first thing you got to realize when working with 3D printing, it usually requires a lot of balancing of engineering requirements and then the project deliverables. It's no different when you're applying it to sterilization. Depending on what numbers you're trying to hit, some of these things might have to be more flexible. So it's just a balancing act, no different than traditional manufacturing, just with slightly different considerations. So for this particular case, we're actually pulling from an HP study, and it's evaluating PA12, their standard nylon material, and evaluating the mechanical performance, the visual performance, and the dimensional accuracy of the components, going through a variety of different sterilization methods. So this graph is essentially indicating that some tensile bars were created and printed in a standard fashion, and then tested as a baseline. From there was different test methods or sterilization methods, one being autoclave at 121C, one being autoclave at 134C. Then formaldehyde was a chemical treatment option. It was supposed to be a similar treatment to kind of the ethylene oxide. So that data point exists. There's electron beam testing at different power levels, and then gamma radiation. So depending on what method you're going through, the results will actually change, and you can see how they change from the baseline here. On average, the tensile strength remained fairly similar for their PA12 product. If we go to the next one, it's evaluating the elongation of break. You see a little bit more variation with what processes are doing to the base material. And this is just here to help you understand if this material and this technology will be a fit for you. Next slide shows a slightly different version where it's the tensile modulus and how that affects, how the sterilization process affects those results. The next one is actually the dimensional accuracy. So this was a test coupon designed with 3 different hole sizes, standard coupon, and run through the same tests. So we have the autoclaves, we have the formaldehyde, we have the E-beams, and then we have the gamma radiation. And essentially, for the measurement being in millimeters, this is quite negligible. So we didn't see a whole lot of dimensional change from the PA12 in this process. Where we see a little bit more interesting results is when we look at the warpage of a part. And this is where the design aspect really comes into play, is designing parts so that maybe they aren't as susceptible to these warping conditions, or they're being used in applications where the warp doesn't matter as much. So essentially a design coupon was created, relatively flat, long part, because that warps the most and becomes easier to measure. And then it was run through the various conditions. Essentially what it's suggesting is as there's more moisture, more heat applied, there's a little bit more warp. All right. Next slide is just a quick look at cosmetic quality. As you put these samples through various processes, you may see visual changes. Usually it's either in color, or in this case, it's some sort of discoloration, identifying that maybe there's some moisture changes in those areas. Those are just things that you would note as you would do with any 3D printed part testing. The last thing that we kind of consider here is the actual potential for the part to absorb any materials. And this is just a sample of what those results could look like. So in an autoclave, when it's steam and heat oriented, you're going to see a little bit more potential for gaining material or absorbing some water. The formaldehyde is in a similar situation where it's a chemistry that potentially can be added, and you have to assess the risk of these percentages for your application to see if it matters. The other ones you don't see as much of an increase purely because you're generally just applying energy. The next slide kind of covers that while you have an initial result on the base material, it's also how you finish these parts. And that's actually going to be the portion that AMT covers nicely here. In general, you have to put this whole workflow together to make it work properly for your application. And so I just kind of came up with 3 kind of closing comments to consider. Essentially, in talking to some of our clients that are really high up in the healthcare industry, their comments were all the requirements for conventional manufacturing still apply to additive. In most cases, additive requires more attention and more considerations because the magnitude of changes that are created with these materials and because of the technologies are greater and probably less understood. The second comment is we are still very early on in the evaluation. So for some perspective, MJF is only 4 years old. Injection molding is over 150 years old. So there's still testing standards being created for this technology and these material sets. And in most cases, there's actually test results still in process. So expect some sort of legwork oriented with these opportunities. But once you break through some of those things, you have an enormous open field to play with. And then the last one is pretty basic. Just use your best practices and pivot when it makes sense. This is essentially you have a design, you want to work with it, select good people to partner with. Forecast3D being an option, AMT also providing solid services, and start from there. Get your idea rolling and see if there's the value that you guys are seeking. So that's my general closing here. I think now's a good time to hand off to Luis. If there's any questions, just let me know.
Thank you, Justin. You know, it's a pleasure to be here with you presenting on this very important topic. I'm the Chief Technology Officer for Additive Manufacturing Technologies, and we've had this great pleasure to collaborate with Forecast in these applications, and especially in these current conditions. It's such an important topic. You know, we have been fortunate to get the support not just from Forecast, but also from HP and other OEMs when it comes to the development and the response that the entire 3D printing community is giving to the shortage of PPE and the development and the production of the future needs from the medical industry, and the response that us as an additive manufacturing community will have and should have. So, you know, to give you an insight on the last point that Justin was touching on, the importance of post-processing and the finishing, it has been highlighted by the current circumstances because of the need to clean and sterilize the parts. So that's where AMT at the moment is having a big impact. And with that, you know, I'd like to introduce you to our portfolio of solutions and our portfolio of offerings. AMT is focused on safe, sustainable industrialized post-processing technology for additive manufacturing. Our vision really is to deploy safe and sustainable solutions that can allow the transition of additive manufacturing at scale. And our goal is to deliver a fully automated digital manufacturing system by 2022. To give you an insight about our company, we're headquartered in Sheffield. We manufacture in Veszprém in Hungary. We don't outsource any of our engineering or manufacturing and development work. We have about 35 employees in Veszprém, which is our workforce site for engineering, development, manufacturing, and deployment of technology for the world. Our offices in the UK serve as the innovation center and rapid deployment of product creation. And we are based in Austin, Texas, here in the United States, which is the headquarters for North America, supporting Canada and Mexico. We have offices also in Taipei, Taiwan, which we recently opened, and we're fortunate to keep expanding and keep delivering these technologies throughout these challenging times. Just to give you an idea of all the different product offerings, I'm going to jump into some of the most recent improvements that we've done, and later we're going to discuss a lot of the results that we've had into some of the third-party testing and share with you the collaboration results that we've had with HP and with others that have been fortunate to allow us to share that information today. But just to highlight the importance of the challenge that we're trying to address is no matter what type of additive technology you're doing, whether it is extrusion, photopolymerization, or powder-based fusion, or selective laser sintering, there is always the need to post-process a part. You need to remove supports, you need to do some sanding, some polishing, priming, vapor chemical deposition. A lot of times there is a significant amount of work that needs to be done before the part can get into use or can be delivered to a potential customer. So I think that is one of the highlights for today from our perspective, is how AMT and the PostPro3D product portfolio can help that particular challenge. When it comes to today's presentation, I think a lot of the focus will be probably on the powder bed fusion results, which is one of the technologies that has been highlighted, whether it is in the production of circuitry components for ventilator parts or for masks and other face shields and personal protection equipment. We've had a lot of support from the industry and from our expanded network of users in sharing some of the results and some of the requirements and success stories that they've had. So just to address this particular technology, these particular challenges, I'm happy to present the sustainable IP-rich portfolio of technologies that AMT has offered. When it comes to post-processing, we start for the cleaning of the part. A lot of the success on the end application will be how carefully you post-process this part, how carefully you clean the part before it gets delivered to the end application, the end customer. AMT has released the PostPro3D, which is the depowdering technologies, and the PostPro3D, which is the surface smoothing technology. PostPro3D allows you to do a fully automated depowdering and cleaning of the part after out of the printer, and it does it in a very sustainable and repeatable manner, so that the variability of the user cleaning, manually cleaning parts individually one by one, it's not just automated and has a faster throughput, but it can also be repeatable, so that the smoothing job down the line is repeatable as well, coming out of the PostPro3D vapor smoothing technology. When it comes to the PostPro3D, we have two different offerings, the standard PostPro3D and the large PostPro, the more industrialized automated version, PostPro3D Pro, which allows you to do a number of automated recipes for different materials, different geometries, and it has the flexibility to also tailor the media so that there is no change in the equipment needs, whether you want to do bead blasting and cleaning or surface treatment and with shot pinning type of applications. You can go from glass beads to ceramic beads or other type of media that you may want to use for a particular finish on a particular application on a given material or part design. All the equipment is ATEX and CE certified, and we can provide you with more information on this particular offering. And as far as PostPro3D, the technology that Justin was referring to is our fully closed loop automated surface smoothing technology. We'll dive a little bit more into the process and how it works, but we have also the Mini, which is a smaller version of the PostPro3D, and also a medical grade machine that has been developed specifically to respond to the needs of the medical industry to be able to deploy it at scale into a production environment within the medical device manufacturing industry. Again, what is unique about our company is the focus on 3 pillars, which is the safety, sustainability, and the scalability of our technology. Safety means that we design everything with the end user in mind, from the design and engineering of the equipment all the way to the chemistries that we use. Sustainability is the focus on the higher purpose to achieve chemistries and technology that is not just eco-friendly, but it's also uses less water, it's got 0 waste, and it just uses better chemistries overall. And the scalability, what we want to do is get rid of the stigma that post-processing has for the additive manufacturing industry, not just on labor, but also on the inability of these technologies to truly communicate and connect with the printers and with other supporting systems within the ecosystem of additive manufacturing at scale. So as far as the post-processing applications within the medical industry, I think is of particular concern these days on how to go about getting FDA-approved medical devices. It's important to highlight that a lot of times our customers ask whether or not our process is FDA approved, or whether one particular technology from AMT, whether our chemistry is FDA approved. I just want to highlight and clarify that the FDA doesn't approve a process. They don't approve necessarily a chemistry. They approve the end product. They approve the device itself. So you do have to go through a very careful process, and the FDA so far has done a great job at providing those guidelines on how to go about approving the specific 3D printed parts. Now, as far as submitting a part that has been treated with our technology, I think that's where we can come in and we can partner with you and share some of the knowledge and some of the experience that we've gained within the last 6 months. It is important to address that, during the focus of today's topic, with PostPro3D, we are going to touch on 4 main topics, 4 main areas of interest. One is the need to eliminate the bacterial growth and address antimicrobial type of concerns, and then also the ability to remove any loose powder or any foreign debris object or anything that has accumulated on the surface of parts, how to reduce the inherent porosity that may come from the processing technology that you're using, whether it's extrusion or powder based, but also the materials that we're using and the settings that are being used, given that settings can give you different processing settings, and different processing conditions will give you different density on your parts. and how to address all the cytotoxicity concerns that they may come from a post-process, given that there is an interaction of a chemistry with the polymer and with the part. Just as an overview, since I've been introducing the PostPro3D surface smoothing technology, I want everybody to know that AMT is using non-flammable, non-explosive chemistries that are not carcinogenic, they're not reprotoxic, they're non-hazardous chemistries as far as a health hazard. Our chemistries have been tested, they are regulated, they're well documented, and we can provide all this information if any one of you has the interest in diving a little bit more into the details of what chemistries we use. At the moment, we are using one chemistry that we have successfully deployed to the market and has been able to treat over 115 different thermoplastics within the additive manufacturing industry. A lot of these polymers, some of them are repeated chemistries, and I'm going to dive a little bit into that later on. But the main point, that the takeaway from this particular presentation is that there is information that is available. There is information that is available in the interaction of our chemistry with different polymer chemistries and their compatibility with the FDA. So far we have not run into any problems. So if the polymer that you're treating is already approved for, let's say, a medical application or for food contact or for skin contact type of applications, our chemistry in the post-treatment with the PostPro3D is not going to affect any of that qualification, if you will. So as far as the PostPro3D Pro, the only difference that we are offering is basically the enhanced safety features that this system offers. It goes well above the existing safety features for the PostPro3D, which, being a closed loop system, it makes sure that the operators are not exposed to the chemistry, but the PostPro3D Pro goes a step further and qualifies that the entire environment, including the supply chains and the storage compartments for the chemistry within a factory floor, are compliant, and we are being constantly monitored for any change in the environmental controls of the machine. We also have an increased memory for the system, so we can build specific recipes and we can save up to 500 different recipes within the system versus 100 different recipes for the standard PostPro3D, and it's got an increased level of security in as far as the user interface and the ability to get different access for different, you can have different levels of operations, just from the regular operator mode to an engineering to an expert maintenance type of access to the controls of the machine. So it's a little bit more open and gives you room for exploration and the different parameters that you can control. As far as the traceability and the logs that you can put out for quality control, quality assurance of traceability of the process and the treatments, is also enabled to communicate and to, do this reporting, but also enabled to communicate with other systems within the factory floor and other MES systems that they may be. It also has the capability to be fully automated, and that's through the partnership that we have with Mitsubishi Robotics. So if you have a part that is got a repeatable design that is changing maybe just in size, but is roughly is the same geometry that you're producing, we have the capability to integrate it with vision systems and robotic arms that will recognize the shape of the geometry. We can enable this automation to do inspection levels from weight changes to surface measurements, all the way to the ability to determine whether or not the part is ready to be post-processed. For example, if there is any residual powder, we're able to do that level of inspection. And to touch a little bit into the process and how it works, for those of you that are users like Forecast, they are already familiar with the process, but it's very simple. It's just 3 stages of the process: the processing stage, the curing stage, and the drying stage. What happens is, we're essentially taking a chemistry in the liquid form, and we are turning it into a vapor that is released inside a chamber that has your parts under vacuum at temperature. And it's a closed loop system where we can control the flow of all these vapors within the chamber, so that we can treat the outer surfaces of a part in a very homogeneous way, as well as the inner cavities and the inner surfaces, which is very, very different, and it's unique to the PostPro3D. There are no technologies out there today that can tailor a very specific RA value. So you have a surface roughness RA value coming out of the printing, whether it is FDM or SLS or multi-jet fusion. PostPro3D will allow you to tailor a specific RA value with because of the ability to control all these processing parameters. And then as soon as the vapors touch your parts, they start dissolving the outer surface of the polymer. At the polymer level, there is a phase change where the polymer goes from solid to liquid and then back to solid. The curing phase is where that phase change from liquid goes back to solid and the polymer is cured. It's safe to the touch, but still there is solvent present. And then during the drying phase, we start extracting all the solvent that they need present, so that by the end of the cycle, which is about an hour and 30 minutes, we are able to guarantee that there is no solvent left on the parts and they're ready to go. There's no need to rinse the parts. There is no need to dry or post-treat the parts in any way. They're ready to be used, and there is no waste. There is no chemical waste. There is no emissions, and there is also no water involved in this treatment. So there are a lot of pluses for the automation that PostPro3D offers, and we can do a lot more. I think if there's interest in learning a little bit more details about the different chemistries and the different things that we can do with PostPro3D, we'll be happy to address this. But so far, we've had a lot of success with rigid plastics and elastomers. We can treat just about every single offering on the filament space, with the exception of perhaps silicone and other high temperature materials like PEEK and PEC that are currently, we're currently exploring solutions for those. But as far as the powder-based technologies, we've had also a lot of success with filled and on-filled systems. So if you have any questions, we'll be happy to answer whether or not PostPro3D will work for your particular offering. We are a company that also prides itself with the ability to respond to the market needs and to remain agnostic to both the OEMs, the process technology, and the materials technology. Our goal is to offer, if you are in the business of additive manufacturing and 3D printed parts, we want to make sure that we are offering a technology that will help you transition from prototyping to production, and from low volume production to large scale, so that additive manufacturing can truly become a competitor against your traditional manufacturing methods. So we work with everybody, and that gives us a lot of advantage, because it puts us in a very strategic point where we can not only influence the material manufacturer, but also the OEMs, so that in collaboration with the end user, we can come up with a joint offering for the end application and your end customer. So let's talk about the performance and the applications for medical. When it comes to what we can do with PostPro3D, the ability to reduce all the imperfections at the surface allows us to, picture this environment where we are able to produce parts that are no longer have the porosity at the surface, all the layering that comes from the layer, the 3D printed process, the layer-wise manufacturing method. So why is this important? When it comes to being able to address the different levels of cleanliness that Justin addressed, cleaning, disinfecting, and sterilizing, I think PostPro3D allows you to address the starting point of this concern, but also the long-term effect, the long-term exposure, and the use and how these parts are going to be used in the field. So, as far as the PostPro3D technology goes, when a part has been printed out of a multi-jet fusion process, for example, it's got a specific surface roughness value that, depending on the orientation of the part or depending on the nesting and the temperature conditions, for example, of your process, you are going to achieve a specific density out of your part. And the reason why there is a lot of variability on the density sometimes is because there are different amounts of residual powder that gets adhered to the surface of those parts. So your surface roughness and your density values are going to be fluctuating a lot based on how many parts you nest and how well are you controlling the thermal conditions of your process. But PostPro3D has the ability, and we're showing it in this graph, to address all the differences that come from the surface and surface imperfection, and control them, normalize them, and do it in a repeatable manner. These different sample numbers that we have there are different parts from different batches printed in a out of the multi-jet fusion process with nylon 12, and they've been treated with different conditions. For all the purposes of this talk, just call it, finish 1, 2, and 3. Call it a light, standard, and heavy finish. But it's just the different parameters within the PostPro3D treatment to be able to achieve a very specific surface roughness value and to do it repeatably. When it comes to the ability to sterilize the surface, it is important to note that, like Justin said, there has been a lot of work done by the OEMs and by the material manufacturers in providing information about the effect of sterilization on 3D printed parts. I mean, there's been a lot of different sterilization processes that have been tried. Whether it is steam, ethylene oxide, then the treatments with gamma rays that Justin was presenting, and there has been very minimal, if negligible, we could argue that is a negligible effect on the performance and the mechanical properties and the performance of the parts. That's great, but that also means that the properties of the mechanical properties and the performance of your parts are no different than as printed. So there's any significant effect on it. You haven't enhanced the performance of the part by the sterilization process. Yes, you sterilize the part, is clean, but it doesn't make it more durable. PostPro3D comes in, and by erasing all the crack initiation sites and all the surface porosity, makes a product more durable. It increases the elongation of break, the fatigue resistance of the product, whether it is a rigid or an elastomeric polymer, and it's able to, as in this graph presents, we've done the testing that this analysis basically has shown that smooth parts have passed the antimicrobial test, showing a significant reduction of bacterial growth, which is quantified as like above 99.5% against the growth of MRSA or E. coli, while the as-printed parts have failed the test, showing a limited reduction for MRSA and significant growth actually for E. coli over time. So this is significant. It means that, you know, your printed parts, yes, they can be sterilized, but over time, you know, the performance of a part that has been treated with PostPro3D with a sealed surface is going to be much better. As far as skin contact, you know, we also have done the third-party analysis to prove that, you know, aside from this, the results that I'm presenting here are specific for nylon 12 from multi-jet fusion again, but depending on the if your polymer has the ability to pass skin contact applications, PostPro3D and our chemistries that we're using are also, you know, they're not going to fail your product. They are also going to be pass the test. And this is also a very significant observation and significant results that are unique to PostPro3D. As far as cytotoxicity, you know, it's basically the ability and the compliance of our chemistries and our process with the ability of not having any no cytotoxic effects. We tested different scenarios. You know, we've talked about how the process treats the parts with the chemistry, and we go through the drying process to extract it. Well, it was important for us to note whether or not the worst possible case scenario, when if the drying process fails, for example, is our chemistry still safe to treat these parts? If a part was fully saturated with Blast-X, which is our the chemistry we're using, the consumable that we use for PostPro3D, what would happen? And even under that scenario, with a part that has been fully saturated with Blast-X, we still are able to pass the cytotoxic testing. And we can share all these results if you are interested in them. But the ability to erase the surface porosity also introduces other, opens the door for other type of applications that include, you know, the ability to eliminate liquid absorption, you know, water absorption, or the permeability to oils or any other liquids, and also gas, for example, gas permeation, and the ability to have any type of oxidation from the exchange of moisture and oxygen between the pores of your part, for example. So the goal has been to produce more durable medical parts, and you can achieve that because you are getting, you know, parts that have material properties that have a higher elongation of break, that are more durable against fatigue resistance, and that, you know, have a better impact resistance, which, you know, we have more data on the fatigue resistance and the impact resistance if some of you may be interested on those. As far as some of the medical studies, like I said, you know, these are some of the examples with using multi-jet fusion nylon 12, some of the masks that have been produced by the industry, and certainly by also by PostPro3D. Orthotics and the ability to have a clean surface, this is where, you know, and also prosthetics is important. The antibacterial properties and the enhanced antibacterial growth that is introduced by PostPro3D, and also dental applications. We got to the end of this presentation, and, you know, I'd like to welcome and open the floor for any questions for Justin or I, and just want everybody to you know, summarize all the benefits from using PostPro3D. So yeah, with that, I'll love to take any questions.
One question I think that's commonly asked out of Forecast 3D and when we're trying to apply your technology is, what are a few tips for designing for your vapor polishing process?
Yeah, do you as a user, do you want to share your insights? I can answer the question. I'd love to hear
Yes.
your.
So I can speak to the multi-jet fusion technology and the materials that are in that range. So for HP's technology, the PA12, PA11, and PA12 glass bead, they all respond somewhat similarly. And the best way you can set it up, a design to run through that process is 1, a uniform wall thickness, 2, a gradual transition between walls, like a fillet or a radius, to allow material to flow more consistently. And then I'm trying to think of the other ones. Having a place to actually hang on to.
Right, and moving parts also.
Yes. One of the things that we can do at Forecast3 is actually evaluate that. That's part of our services, is to look at the design for additive. And we've worked with customers to optimize their original parts for this post-processing, and actually do 2 things. One is improve the quality of the part as well as drive down the cost. We've had success with that. I can also say that there's additional materials, the BASF 88A TPU, that polishes very well. You get some very exciting results out of that. The PA11 also, it tends to increase the ductility and becomes very flexible. So that there's some interesting properties there for maybe orthotics or other applications where you need more durability in the hinge-like functions or the ductility aspect of things. We also noted that there is no current solution to the Lubrizol 95A TPU. So that's something to keep in mind, as well as the polypropylene. I believe you had an asterisk on the polypropylene in your presentation. But those are the things that we noted with the MJF technology so far.
Correct. And great point on the design for additive manufacturing. If you're already taking all of those considerations, you should never forget about the need to post-process. So you need to design for post-processing. I think it's important that, any small parts, like you said, the idea is to automate this and to make it as affordable as possible. And any small parts, if you can design them so that they are easily clean, and that they are easily smooth at the same time. So there are different techniques that different users have applied, and but as far as our process, it's very flexible and very forgiving to the geometries, and we can help you, address any of those concerns. We can share the design.
Yes, and my last comment there is AMT has been a great resource to work with. They have an application engineer, specifically Brad, who's been fantastic at responding and developing recipes for customers. If you guys find a need to experiment with this technology or have an application that you want to learn more about, I believe either between Luis or myself, we can come up with some avenue to create a solution for you.